Welcome back to The Deep Dive, the show where we cut through the noise and get straight to the knowledge that truly matters in the world of technology.
Great to be back.
Last time, we explored the fascinating world of multi-agent systems, or MAS, how intelligent agents can collaborate to solve complex problems.
Yeah, that was a good one. How they work together.
Today, we're taking an even deeper dive, not into their interactions with each other, but into their very core, the internal mind of the agent itself.
Indeed. We're peeling back the layers to understand what makes an AI agent truly smart, not just reactive. We're talking about the cognitive engine, memory, attention, and reasoning in agents.
The cognitive engine, I like that.
Right. This is where an agent transcends being, a simple automaton and starts becoming a context-aware partner, capable of genuine understanding and adaptive behavior.
So moving beyond just following instructions.
Yes, exactly. Understanding these three core faculties, memory to learn from experience, attention to focus on what matters, and reasoning to draw conclusions is absolutely critical for anyone, from students to seasoned tech enthusiasts interested in building or understanding truly autonomous AI systems.
That's a perfect setup. Our mission today is to delve into the internal mechanisms that allow an agent to think, to really get into its digital mind. And to guide us through this intricate landscape, we've structured this deep dive as a comprehensive Q&A. To give you, our listener, a roadmap for our journey today, here are the core questions we'll be tackling.
Okay, let's lay them out. First, how do we create agents that can actually learn and maintain context over time? That's crucial.
Right.
Second, what exactly is working memory in the context of an AI agent?
Okay.
Third, what is episodic memory and what role does it play, the long-term stuff?
Got it.
Fourth, what's the main challenge with that episodic memory and what's the key technique used to solve it? There's a big one there. Fifth, how does RAG work? You hear that term a lot. And what are these vector databases?
Yeah, R's and vectors. Need to unpack that.
Sixth, can you walk us through the full Retrieval-Augmented Generation process? Like when a user asks a question, what actually happens step by step?
Okay, the practical flow.
Seventh, once the agent has all this information in its working memory, how does it know what to focus on?
Good question. Attention, maybe.
You're jumping ahead. Eighth, how does this attention mechanism, as you hinted, directly contribute to an agent's overall context awareness?
Okay, linking attention to context.
Ninth, how are developers able to practically implement these powerful but complex cognitive concepts? The tools.
Hero.
10th, what is the practical process for building an agent's episodic memory? The document calls it semantic indexing. What's involved?
Semantic indexing, all right.
11th, shifting gears slightly.
Yeah.
What is the classical rule-based approach to AI reasoning? The old school way.
Go FAI.
Exactly, Joe FAI.
Right.
12th, what are the main strengths and weaknesses of that classical symbolic approach?
Pros and cons.
13th, how does the modern approach of reasoning with LLMs work? And what are its pros and cons? The new way.
The LLM way.
And finally, 14th, to bring it all together.
Yeah.
How do memory, attention, and reasoning combine to form this cognitive engine we're talking about? The big picture.
That's quite the blueprint. An excellent overview of what's coming. Let's get right into it, starting with that fundamental concept, memory.
Absolutely. So to begin, you mentioned memory. How do we create agents that can learn and maintain context over time?
Yeah, how do we get past that forgetfulness?
Well, the fundamental limitation of early AI systems, particularly conversational ones, was their inherent amnesia.
Like Dory from Finding Nemo.
Kind of. Imagine a sophisticated chatbot. It could engage in a brilliant, complex conversation, only to have zero memory of anything that was just discussed moments later.
Rush.
Totally. Every new interaction was like meeting you for the very first time. So to move beyond this, to create agents that genuinely learn and maintain context over extended periods, maybe across multiple sessions or even days, we absolutely must implement different types of memory systems.
Okay, different types, like human memory.
Exactly. The analogy holds up pretty well. We're primarily talking about two types: working memory for short-term, immediate tasks, and episodic memory for long-term persistence and learning. Without these, an agent is just, a stateless automaton. It can't really grow.
So an AI without memory is stuck in an eternal present, unable to learn or grow. That makes sense. Let's dig into that working memory first. What exactly is working memory in the context of an AI agent?
Right. Working memory. You can think of it as the agent's active computational space. It's the information the agent is actively processing and sort of thinking about right
Or
now.
the mental scratch pad.
That's a great way to put it. For agents built on large language models, LLMs, this pretty much directly corresponds to the model's context window, that limited space.
Ah, okay. The context window is the working memory, essentially.
For the most part, yeah. This memory holds the immediate history of the current conversation, the user's latest query, and any data the agent has just retrieved for immediate use, like for Raji.
So what defines it?
Its primary characteristics are that it's very fast to access. But crucially, it's limited in size and entirely transient, temporary.
Transient meaning.
Meaning, once the conversation ends, or if the context window gets full and older information is pushed out, that data is just lost, gone.
Okay, and its purpose?
Its core function is to maintain coherence and context for the immediate task. It allows the agent to understand things like pronouns, knowing what it refers to, follow multi-step instructions, and just remember what was said a minute ago within the active interaction. It's the agent's immediate awareness,
That's a clear picture of its immediate awareness, very much like our own short-term recall. So if working memory is temporary, what then is episodic memory, and what vital role does it play? This sounds like the more permanent store.
Exactly. If working memory is the fleeting now, episodic memory is the agent's permanent, ever-growing historical archive. Its library of past experiences.
Okay, what kind of things go in there?
This is where an agent stores key facts, maybe summaries of previous conversations, any learned knowledge that should persist over time beyond just a single interaction.
And the benefit, why is this so important?
Well, an agent equipped with episodic memory gains a profound capability. It can remember a user's specific preferences from a month ago.
Ah, personalization.
Big time. Or recall a successful solution to a problem it solved last week, and truly build a cumulative understanding of its world over time. Its function is really to enable continuous learning, personalization, and long-term consistency. It essentially gives the agent a sense of history and maybe even a unique identity, in a way.
That's powerful. So it's like its own personal knowledge base.
Pretty much. While it's vast in capacity and persistent, it's also slower to access than working memory. It requires a deliberate process of storage and retrieval. You have to actively put things in and pull things out.
So there's a trade-off. Capacity versus speed.
Absolutely. And the most effective agents, you see, they dynamically use both. They strategically load relevant information from their long-term episodic memory into their short-term working memory to handle the current task with the full necessary context.
It sounds like having a vast external brain that the agent can consult as needed.
Sure.
Smart. But if it's vast, that immediately brings up a challenge. How do you find anything relevant in it quickly? So that leads us to the next point. What is the main challenge with episodic memory, and what is the key technique used to solve it?
You've hit on the critical bottleneck. The central challenge with episodic memory is precisely that retrieval at scale.
Finding the needle in the haystack.
Exactly. Imagine an agent that has accumulated millions, maybe billions, of past experiences, documents, conversation snippets. How can it efficiently search through this potentially enormous, unstructured library to find the specific memories that are truly relevant to the current situation or user query?
Yeah, that sounds computationally expensive.
It's a massive data retrieval problem, where the haystack is constantly growing. The answer, and a truly powerful technique that has, frankly, revolutionized LLM applications, is called Retrieval-Augmented Generation, or RAG.
RAG. Okay, we hear that acronym constantly. How does RAG work? It sounds like it involves something called vector databases. What's going on under the hood?
You're absolutely right. Vector databases are at the heart of RAG. The whole process begins with something called vector embeddings.
Embeddings, right. Turning words into numbers.
Essentially, yes. All of an agent's memories, whether they are text, documents, maybe even images or audio logs in the future, are converted into a mathematical format. This is done using an embedding model, which transforms a piece of data into a high-dimensional vector.
A long list of numbers.
A very long list of numbers. Think of these vectors as numerical representations that capture the semantic meaning of the text, not just the keywords.
Okay, semantic meaning. What does that enable?
Well, the true innovation here, this sort of magic, is that semantically similar concepts are positioned very close to each other in this high-dimensional vector space.
So things that mean similar things are neighbors in this math space.
Precisely. For instance, the phrases Toronto's weather and climate in Ontario's capital would generate remarkably similar vectors because they convey the same core meaning, even if the actual words used are quite different.
Okay, that's cool. So you have these meaning vectors. Then what?
Once we have these vectors, they are stored in specialized vector databases. These are purpose-built databases, things like Pinecone, Chroma, Milvus, Weaviate. There are quite a few now, which are uniquely designed to do one thing exceptionally well: store potentially billions of these high-dimensional vectors and perform incredibly fast similarity searches.
Similarity searches, meaning finding the closest vectors.
Exactly. So when the agent needs to recall a memory, it takes its current query, converts that query into a vector using the same embedding model, and then asks the vector database, find me the memory vectors that are closest or most mathematically similar to this query vector. This allows for incredibly fast and semantically relevant retrieval, far, far beyond what traditional keyword searches could ever achieve.
That's a clear explanation of the underlying mechanism. Really clever how it uses spatial proximity for meaning. So once these similar memories are retrieved, how are they actually integrated? Can you walk us through the full retrieval-augmented generation process when a user asks a question, like the play-by-play?
Certainly. When a user asks a RAG-enabled agent a question, the agent doesn't immediately try to generate an answer based solely on its internal LLM knowledge, its pre-trained data. That's key.
Okay, it doesn't just guess.
Right. Instead, it follows a robust two-step process to ensure accuracy and contextual relevance. Step 1 is retrieve. The agent takes the user's query, converts it into a vector, and then uses that vector to search its vector database, which, as we discussed, holds its episodic memory, to find the most relevant documents or past memories related to the query. And again, this isn't just finding exact keywords. It's about finding information that is semantically similar to the user's intent, what they mean.
Okay, so it fetches the relevant context first, then step 2.
Step 2 is augment and generate. Once the relevant information is retrieved, the agent doesn't just pass the user's original question directly to the LLM. This is the augmented part. Instead, it takes the original user query and strategically injects the retrieved information directly into its prompt, explicitly as context for the LLM.
Ah, it stuffs the context into the prompt window.
Pretty much. For example, the prompt might become something like, using the following context. Here's that retrieved memory about the user's previous project details. Answer the user's question. Here's the original question about the project. This whole augmented prompt is then sent to the LLM.
I see. So the LLM gets the question plus the relevant facts from memory all at once.
Exactly. And RAG is truly revolutionary because it grounds the LLM in specific, often verifiable facts from its memory or provided documents. This dramatically reduces instances of hallucination, where LLMs confidently state false information.
Yeah, the making stuff up problem.
Right. RAG allows the agent to provide accurate, up-to-date, and potentially highly personalized information directly drawn from its own vast memory or specific knowledge base, rather than relying solely on its pre-trained, generalized, and possibly outdated knowledge.
So the agent now has all this rich context in its working memory, the recent chat history, plus the relevant episodic memories pulled in via RAG. But with potentially so much information now, how does it then know what to focus on within all that data? It sounds like it could get overloaded.
That's precisely where the attention mechanism comes in, and it's a truly foundational concept in modern AI, particularly within the transformer architecture that powers, well, pretty much all the large language models we use today.
Attention. Okay, sounds intuitive, but what does it mean technically?
At its core, an attention mechanism allows a model to dynamically weigh the importance of different parts of its input when it's generating an output.
So prioritize certain words or pieces of info.
Exactly. Instead of treating every single word or piece of information in its context window, its working memory equally, it learns to pay more attention to the words, phrases, or even retrieve data chunks that are most relevant to the current task or the specific question being answered.
Like highlighting the important bits.
That's a perfect analogy. Think of it like a highly efficient internal spotlight that shines brighter on the most salient information, allowing the model to prioritize and process what truly matters in that specific moment, while sort of dimming the less relevant stuff.
A dynamic spotlight that's a powerful visualization. So how does this attention mechanism directly contribute to an agent's overall context awareness? How does that spotlight help it understand the situation better?
Well, that dynamic spotlight directly translates into sophisticated context awareness within an agentic system. Imagine an agent's working memory, right? It might contain the last 10 turns of a long conversation, plus several detailed documents just retrieved via RLA.
Yeah, that's potentially a lot of text.
A significant amount of information. The attention mechanism within the underlying LLM is what enables the agent to expertly sift through this entire, potentially overwhelming context. It allows the agent to focus laser-like on the specific sentences, facts, or data points, whether they come from the recent conversation history or the freshly retrieved memories, that are most critical for formulating its next action or response.
So it filters out the noise.
Precisely. This capacity gives the agent the crucial ability to dynamically determine what is truly signal and what is merely noise within its current information landscape. And that leads to far more coherent, relevant, and frankly intelligent behavior. It's about focusing resources.
These concepts sound incredibly powerful, almost like we're architecting a synthetic brain here, but they also sound quite complex to implement from scratch. How are developers actually able to practically implement them in real-world applications? Is this only for giant tech companies?
That's a great question, and the good news is, thankfully, no. These sophisticated cognitive concepts are no longer just theoretical lab experiments. The rise of robust open-source frameworks has made them eminently practical for developers, even small teams or individuals, to implement.
Okay, frameworks. Like what?
A leading example in this space, one you hear about constantly, is LangChain.
LangChain, yeah, definitely heard of it.
It's an incredibly popular open-source framework specifically designed for developing applications powered by large language models. It essentially provides a rich set of modular components, building blocks, that streamline the process of building complex agentic systems, like Lego for LLM apps.
Okay, so it simplifies things. How does it help with memory, specifically?
Well, specifically for memory, LangChain offers a variety of pre-built memory modules. These make implementing agent memory much more straightforward, handling a lot of the tricky underlying logic for you.
Examples.
Sure. There are simple buffers for managing working memory, like conversation buffer memory, which just keeps track of recent turns. And there are more sophisticated modules that can automatically summarize conversations as they happen and then store those summaries in a long-term memory store, perhaps linked to a vector database.
Ah, so it handles the saving and loading.
Exactly. These modules abstract away a lot of the complexity. They handle the logic of loading relevant memory into the agent's context before it acts, and then saving new information or summaries after an interaction. It significantly accelerates development time.
So LangChain simplifies the memory management, making these advanced capabilities much more accessible.
That's good to know.
Huh.
You also mentioned episodic memory and building that searchable index. What is the practical process for building an agent's episodic memory, which the document calls semantic indexing? What are the steps involved in creating that AIagent-ready memory?
Right, semantic indexing. It's indeed the practical term for the process of systematically building that searchable episodic memory, that long-term knowledge base for the agent. It involves a pretty clear multi-step pipeline for preparing data for retrieval via AIagent.
Okay, what's step one?
First, you start by taking a collection of documents or various data sources. Could be PDFs, text files, database entries, website content, anything you want your agent to learn from and remember over the long term.
Your raw knowledge.
Exactly. Second, you break these potentially larger pieces of information down into smaller, more manageable chunks.
Why chunk? It's important for a couple of reasons. LLMs have context window limits, so you need chunks that fit. Also, smaller, more focused chunks generally allow for more precise retrieval later on. You retrieve just the relevant paragraph, not the whole chapter.
Makes sense. Okay, so you have chunks then.
Third, you use an embedding model, like the ones we talked about earlier, to convert each of those chunks of text into a high-dimensional vector. That numerical representation capturing the meaning.
Embedding everything.
Right. And finally, fourth, you store all of these generated vectors, along with perhaps the original text chunk or reference to it, in a specialized vector database.
Populating the vector store.
Exactly. This last step is crucial because it creates the actual searchable index that R can then query very rapidly and efficiently using vector similarity search. And tools like LangChain, as we just discussed, often have built-in integrations with various embedding models and vector databases, which really helps streamline this entire semantic indexing pipeline for developers. Makes it much easier to set up.
That brings us nicely to the third core pillar of an agent's cognitive engine, reasoning. Now, when we talk about AI reasoning, there are actually different approaches, aren't there? What is the classical rule-based approach to AI reasoning? The older style.
Yes, the classical approach. It's often referred to as symbolic AI, or sometimes, quite endearingly, as you mentioned earlier, good old-fashioned AI, Go FAI.
Go FAI. Love that term.
Me too. In this paradigm, knowledge is represented very explicitly. Think of it as a set of defined facts in clear logical rules, often in an if-then format. For example, a rule might be explicitly stated as, if X is a human, then X is mortal. A fact might be, Socrates is a human.
Very structured.
Extremely structured. Reasoning is then performed through a process of logical deduction or inference. You have a reasoning engine, often called an inference engine, that applies these predefined rules to the known facts to derive new conclusions. So given the rule and the fact, it could deduce Socrates is mortal.
Like mathematical logic.
Very much so. It's a very structured, deterministic, and precise way of thinking, almost like executing a meticulously crafted flowchart or a formal proof.
So it's very precise and logical, which sounds good, but perhaps a bit rigid. What are the main strengths and weaknesses of that classical symbolic approach to reasoning?
You're exactly right. Precision is a key strength. Its main strengths are that it's highly precise, its deterministic meaning, given the same facts and rules. It will always reach the same conclusion, and crucially, it's incredibly explainable or interpretable.
Explainable how?
When a conclusion is reached, you can literally trace the exact chain of logical rules and facts that led to it, step by step. This provides complete transparency, which is invaluable in domains where auditability and trust are paramount, like maybe finance or medical diagnosis assistance.
Okay, those are solid strengths. But the weaknesses, you mentioned rigidity.
Yes, the weaknesses are significant, especially for dealing with the complexities of the real world. It's notoriously brittle. Brittle means it struggles immensely with ambiguity, nuance, uncertainty, or common sense things humans handle effortlessly. It also breaks down easily if it encounters a situation that isn't explicitly covered by its predefined rules.
So if it hasn't been explicitly told what to do?
It often just fails.
Yeah.
It's a bit like having an incredibly brilliant but incredibly literal-minded colleague. Ask them anything slightly outside their strict rulebook and they can't compute. Furthermore, creating and, more importantly, maintaining a truly comprehensive rule set for any complex real-world domain becomes an incredibly difficult, often practically impossible task. It just doesn't scale well or adapt easily to the messy, nuanced reality of the world.
That brittleness definitely sounds like a major limitation for many real-world applications. And that leads us directly to the modern era, the rise of deep learning. How does the modern approach of reasoning with LLMs work, and what are its pros and cons? How do these giant neural networks reason?
Right. The modern approach, which falls under the umbrella of connectionist AI or deep learning, is fundamentally quite different from symbolic AI. An LLM doesn't possess an explicit, predefined set of logical rules like Joe FAI systems do.
So no if-then statements coded in?
Not explicitly, no. Instead, it reasons by leveraging the immense statistical patterns and relationships it has learned from processing truly vast amounts of training, data text, code, conversations from the internet, books, etc. When an LLM is given a problem or a prompt, it generates a solution or continuation that is statistically probable based on the billions, even trillions, of examples and patterns it observed during its training.
So it's more about predicting the most likely answer based on patterns?
In essence, yes. It's less about explicit logical deduction and more about sophisticated pattern matching and generation based on statistical likelihoods learned from data.
Okay, so what are the good points, the strengths of this approach?
Its main strengths are its remarkable flexibility and sometimes creativity. LLMs can handle nuance, ambiguity, and apply a form of common-sense reasoning with often impressive effectiveness. They can generalize across diverse topics and situations in a way symbolic systems really struggle with. They can generate human-like text, summarize complex information, and even engage in creative tasks.
That flexibility sounds powerful, but the downsides, the weaknesses?
They come with significant weaknesses too, absolutely. As we touched on with RAG, they can be unreliable and are prone to hallucination.
Right, confidently making things up.
Exactly. Confidently stating false or nonsensical information as if it were fact, because statistically, it looked plausible based on patterns in the training data. Furthermore, their reasoning process is often described as a black box.
Meaning we don't know how it got the answer.
It's very difficult, often impossible, to understand why a particular output was produced or trace the exact chain of thought it followed in a verifiable way. This lack of explainability is a critical challenge for applications where trust, transparency, and accountability are paramount. You can't easily audit its reasoning.
So powerful but potentially unreliable and opaque. That's a key trade-off.
It absolutely is. And it's worth noting briefly that some of the most cutting-edge research in advanced agent architectures today are actively exploring what are called neuro-symbolic approaches. These try to combine the strengths of both worlds, leveraging LLMs for their flexible understanding and common sense, while using symbolic engines for logical consistency, factual grounding, and perhaps constraints. Trying to get the best of both.
Fascinating. Merging the old and new. Okay, this has been an incredibly insightful deep dive into the inner workings of AI agents, really dissecting their cognitive core memory, attention, and reasoning. Now, to bring it all together for our listener, how do memory, attention, and reasoning combine to form an agent's cognitive engine? What's the synergy here? How do they all work together?
They really are the trifecta, aren't they? They are the fundamental building blocks that, working together, elevate an agent from being a simple reactive script to potentially a truly intelligent adaptive system. Each piece plays a critical, interconnected role in that engine.
So walk us through that interplay.
Okay. Memory, both the short-term working memory and the long-term episodic memory, provides the agent with crucial context. It gives it the ability to learn from its past experiences, preventing that frustrating amnesia we talked about, and allowing it to build a persistent understanding of its user and its world over time.
The foundation of context and learning.
Exactly. Then, the Retrieval-Augmented Generation, RG technique, powered by those specialized vector databases, is the practical, scalable mechanism that allows an agent to efficiently access and leverage its vast long-term memory. It grounds the agent's responses in specific facts or past experiences when needed.
Making memory usable at scale.
Right. Next, the attention mechanism acts like the agent's internal spotlight. It dynamically allows it to focus on the most relevant information within its current context window, which contains both working memory and potentially RG retrieved data. It effectively distinguishes the important signal from the background noise, ensuring coherent and focused behavior.
The focus filter.
Precisely. And finally, reasoning, whether it's the precise deduction of classical rule-based approaches or the flexible, common-sense pattern recognition of modern LLMs, defines the very character of the agent's thought process. It dictates how it derives new conclusions, makes decisions, or plans its actions based on the information it is remembered and focused on.
The thinking part.
Yes, the core processing. In essence, these faculties working in concert allow an agent to move far beyond simple perception action loops, like a thermostat. They enable a much more sophisticated cognitive cycle. The agent can perceive its environment or a user's request, then remember relevant past experiences or knowledge using AIEG, focus its attention on the most critical information, reason about that information to form a plan or generate a response, and then finally act.
Perceive, remember, focus, reason, act. That's a much richer loop.
It's a much richer loop. And that synergy is what makes possible the creation of more autonomous, personalized, and profoundly capable AI systems. It's how we move from simple tools towards potentially powerful collaborators in tackling complex problems. We're truly building intelligence piece by cognitive piece.
What an incredible journey through the cognitive architecture of AI agents. It really shows how these systems are becoming more sophisticated, moving beyond simple pattern matching. The foundational role of memory, both working and episodic for context and learning. It's now undeniably clear how vital that is.
Absolutely essential.
And RA's importance for efficient long-term memory retrieval, that's revolutionary, really solving a huge scaling problem for making memory practical.
A game changer.
We've also seen how attention mechanisms are crucial for that dynamic content awareness and focus, letting the agent zero in on what matters, and how the distinct approaches to reasoning, classical logic versus modern LLM inference, define an agent's actual thought process and its strengths and weaknesses.
Different styles of thinking, in a way.
Exactly. It's so evident that these cognitive architectures, memory, attention, reasoning, working together are absolutely essential for building truly intelligent and capable AI agents that can actually learn, adapt, and operate autonomously.
And this journey into agentic AI is really just getting started. It's far from over. Join us next time on The Deep Dive as we explore the agent's handshake, language, tools, and environment interaction.
Ooh, the handshake. Sounds intriguing.
Yeah, we'll dive into how these sophisticated agents, now that we understand their internal minds a bit better, actually move beyond their internal processing to interact with the real world or the digital world. How they use tools, communicate effectively with us, and maybe even interact with other systems or APIs.
So how they actually do things. Can't wait for that.
It should be fascinating.
We definitely can't wait to share that with you. For now, thank you so much for joining us on this deep dive into the cognitive engine of AI agents. It's been incredibly informative.
My pleasure.
And to you, our listener, be sure to subscribe to our channel, Tech AI and Beyond, to stay informed and continue your journey into the fascinating, fast-moving world of artificial intelligence. We'll see you next time.